And thanks everyone for coming to this slightly early morning presentation. Today I'm going to talk about finding and fixing security bugs in Adobe Flash. I've been working to improve the security of Flash for over a year now. So I wanted to share with everyone how that year went, what sort of bugs I found, what sort of exploits turned up in the wild, and what sort of mitigations were implemented to prevent them. But before I begin, who am I? I'm Natalie Silvanovich, and I'm a security researcher on Google's Project Zero. Project Zero is a team at Google that works to reduce the impact of 0 days in the wild. And I specifically work on Flash, trying to reduce the impact of 0-day vulnerabilities there. Before I worked on Project Zero, I worked in mobile security for about 5 years. And something that a lot of people don't realize is that up to about 5 years ago, back in the dark ages, it was really common for virtual machines to be the root of trust on a mobile device. The most common one was the Java virtual machine, but a lot of other virtual machines were used too. In fact, there was even a BlackBerry device, the BlackBerry Playbook tablet, where the main VM was Adobe Flash. So that's how I really got into Flash. Now I would describe myself as a Flash enthusiast. I love finding bugs in Flash, I love making the sad puzzle piece appear, and currently I report about 1/3 of Flash vulnerabilities. So what's the problem I'm trying to solve? Well, bugs. Lots and lots of bugs. I have the classic headline slide here with every problem that Flash vulnerabilities have caused. You have high-level state attackers, you have financially motivated attackers, you have malware served through ads, you have ransomware. Basically, any attack you can think of that involves compromising a user's host, a Flash vulnerability has been used for it at some point. So I was hoping to try to make an impact on this problem and reduce the number of vulnerabilities that were found in the wild. Here's another sample of what the landscape looks like. This is a timeline of the year, and I've got kind of the good guys at the top and the bad guys at the bottom. So you can see there were many Flash updates and a few mitigations implemented, and then you can see the timeline of 0 days on the bottom. And depending on how you count, there were at least 7 last year. So it seems every few months a 0-day turns up in the wild, and that's just what we know about. So what's kind of the technical problem here? Sometimes I think people are a little too quick to bash Flash for having bugs in it, because really what has led to this is just how widespread Flash is. If you attack a browser, well, the user might have different browsers. And that's the same with lots of software. Not everyone has it installed, but almost everyone has Flash installed. So it makes it a tempting target, regardless of whether an attacker is trying to attack one person and doesn't know a lot about them and hopes they have this installed, or if they're trying to do a widespread attack and compromise a lot of people. Flash can be very valuable because almost everyone uses it. And there are a few other aspects of Flash that make it a good target. There are indeed a lot of vulnerabilities being found in it. And also, attackers can easily exploit vulnerabilities. And I have easily asterisk that's comparative to other software, and this has improved a lot over the last year. But up to about last August, there was a limited number of mitigations in Flash, and it was fairly easy to exploit. So what am I going to talk about today? I'll start by going over what Flash is and the attack surface, and then talk about reducing vulnerabilities in Flash. Then I'll talk about exploit mitigations that got implemented, and then I'll go through a bit the future of Flash, where I think Flash bugs and exploitation are going. So to start off, I'm going to do a quick overview of what Flash is and what the problem is I'm trying to solve here. So Flash is a browser plugin. And the way it starts is there's a developer that writes code in Actionscript. That's the script language that is supported by Flash. And they use a Flash compiler, and many of them are available, and they create a Swift file. And then the Swift file is hosted on a website. And then a user visits the website, their browser downloads it, and then the Flash plugin will parse this Swift file and display content to the user, like videos and audio. And then the user has a wonderful web experience. Rainbows appear as they enjoy their game or their music or whatever. Now, the problem I'm trying to solve is that there is a malicious developer who writes a malicious Swift, usually an Actionscript, though sometimes they'll write a Swift directly. And then they put it on a website. And it could be a malicious website they own, or they could have somehow compromised someone else's website. But regardless, they convince the user to browse there, and then the browser downloads the Swift, and then the Flash plugin parses the Swift in such a way that it leads to arbitrary code being executed, even though the Flash player doesn't normally allow this. And then the user is very sad because they've been compromised. And the reason I'm showing these slides is just I want to be very clear on the problem I'm solving here. There definitely are some other problems with Flash. For example, sometimes the Flash developer writes a vulnerability in the Swift file, and that is a problem, but not the one I'm trying to solve. Also, there have been cross-domain or browser policy issues with Flash where the Swift file tries to access other parts of the web that it shouldn't be allowed to access. And that's a different problem, but it's not an especially common one. The vast majority of Flash attacks follow this pattern where someone finds a memory corruption vulnerability in Flash and uses it to execute code. So I talked about Actionscript being compiled into a Swift. What actually is a Swift? It has a few components. As I said, the most important component is the script that the developer writes. And there's two types of script that's supported. There is Actionscript II, which was the original Actionscript language, and it was eventually deprecated in favor of Actionscript III. But since Flash has to support all Swifts that have been created on the web ever, it still supports Actionscript II, but these are completely separate. You either write an Actionscript II Swift, and then you have to always use Actionscript II, or you write an Actionscript III Swift. You can't combine the two languages. And other things that might be in a Swift include metadata, so things that say where the script is, images, music, fonts, and they also contain something called frames. And this is where, in the development environment, you can actually draw stuff and create an animation and go from frame to frame. And a lot of Swifts use this feature a lot and only have a minimum of script. It depends on what tool you use to develop it. But that's another feature that supported the ability to make dynamic frames and go from one frame to another. So from a virtual machine perspective, from the Flash plugin perspective, it consists of three main components. The first one is the Actionscript II VM, as I mentioned. And this is the old interpreted VM. It is just a huge while loop. And if it needs to call into a native API, well, it just branches out of the while loop and branches back. It has a reduced API set because it only supports the APIs up until when it was deprecated. And I would say it generally has more bugs, but with lower exploitability. The thing with Actionscript II is it was written before what I'd call the modern security environment. So they made a lot of decisions that would not have been made today. For example, if you write a native API for Actionscript II, you have to manually check the type of every single parameter that gets put in. And that was because, I guess, they weren't expecting malicious people to try and put in bad parameters. And this sort of thing is hard to fix once it's been implemented. So there's often a lot of bugs in Actionscript II. But the flip side is they tend not to be as exploitable. Because the thing about Actionscript II is there's not as much stuff in there because it doesn't have as many features. So let's say you have an overflow vulnerability and you're trying to find that perfect object to overflow to exploit it. It's less likely to exist in Actionscript II. And some people who write exploits try to get around this by having an Actionscript III Swift and then loading an Actionscript II Swift. And this sometimes works, but it doesn't always work. There are sometimes bugs that have a very narrow window. For example, there's a pointer and then it gets freed, then it gets used, and then it goes out of scope. And in that case, it's not possible. So in Actionscript II, it can generally be more difficult to exploit a bug. Actionscript III is the answer to Actionscript II. It is Flash's modern VM. It has just-in-time compilation and an interpreter. And something cool about it is it's open source. So if you go on the Tamarin project on Mozilla, you can actually see the Actionscript III VM. And it's extendable. So the way you write native code in Actionscript III is you declare an Actionscript API, and there's very clear boundaries. And it's quite easy to extend it. It also has two heaps. There's a garbage collected heap that I describe as conservative, non-strict, non-exact. It takes a while for things to get freed, and you generally don't have the problem with stuff getting spuriously freed, but it does happen eventually. And then there's a fixed heap, which is used for really long-lived objects, for example, frames and bitmaps and that sort of thing. And this is all optimized by Flash for Flash, but as I said, you can use it for anything. You can also find the heap on Mozilla. The project is MMGC. And with regards to actual Actionscript III APIs, things like arrays, vectors, strings, and that sort of thing, the really common ones you can find in the open source project, but the proprietary ones, things like, I don't know, image filtering, are proprietary to Adobe and you can't get the source. And I'd say in general, bugs in Actionscript 3 are less dense but more exploitable. It's fairly hard to find a bug in Actionscript 3 these days because it has a lot of features that prevent bugs. But if you do find one, it tends to be very exploitable because you just have so many Flash features to use in your exploit. And the final portion of Flash is what we like to call the Anticorpus. And this is the functionality outside of script, things like the MP4 parsers, edlib, regex, image decoders, all that stuff. So when I talk about Flash vulnerabilities, what sort of vulnerabilities tend to happen in Flash? The most common one, as I said, is bugs that allow loading a Swift execute code. And typically these are memory corruption bugs, though there have been others. Just to give a brief overview, these are the types of vulnerabilities I'll show you today. There's the general overflow class, which is you have a small buffer and you copy a large buffer into it, and then you can overflow onto the heap or the stack. There are use after frees, where you have a buffer and then you delete it and then you do something with it. And especially in Flash, it can be fairly easy to move that into a state where the buffer is reallocated and you have two different places in the code contending over that buffer, and that can lead to code execution. And another type of bug that's really common in Flash, and I'd say common in script engines in general, is type confusion. And that is where you create one type of object and then you cast it to another type and you start calling stuff. And since you have basically the wrong vtable in there, it leads to all sorts of weird function calls that can often lead to code execution. So what's my goal here? I want to find all of the Flash bugs. I want to find every last one, and then sometime around 2022, I will have found the last Flash bug, and that's it. Flash will be secure. Now, obviously, this isn't a very realistic goal. What I really want to do is make Flash better. My current priority right now is finding bugs. While I might not find all of the bugs, I want to find enough bugs that it decreases the bug density and makes it more difficult for other people to find bugs. I mostly do this through code review, though I do some fuzzing with my colleague Matthias Hurek. When I started, I was finding one bug per day, and now I'm down to about one bug per week. And something I wanted to mention is that bugs in Flash, once they're fixed, they stay gone. Something people ask me fairly often is, do you think you're finding bugs faster than they're being added? And the answer here is definitely yes, because development on Flash has stopped, so they're not making any new bugs. So this is really a unique opportunity to reduce the bug density by finding bugs, because we know they're not putting any more in. Something else I do is I spend a lot of time analyzing external bugs and exploits. I don't just want to know about my bugs. I want to know about every bug in Flash so that I can understand how they happened and how they were exploited, and then both find variants of those bugs and also think about mitigations that might prevent the exploit. I also occasionally exploit bugs to answer questions. For example, is exploitation possible? Is it reliable? And how do certain factors impact exploitability? And also my team, mostly my colleagues James Forshaw and Mark Brand, works on mitigations. We worked with Adobe to try and put in mitigations that make the most common types of exploits less likely to happen. So I'm going to start off by talking about how to find a Flash bug and the different ways that people find them. There's three main options here. There's code review, IDA, and fuzzing. And one way to do this is through code review. The benefits of code review is they find deep, unusual bugs, but the downside is that they require source, though a lot of Flash is open source. And it is a bit of an upfront investment. When you start looking at the code, you do have to look at it for quite a while before you understand it, but I think once you do, you can pick out bugs quite quickly. To give you some examples of bugs that I've found through code review, to start off, there's this issue, which I call the Convolution Filter issue. And what's interesting about this one is it was independently discovered at least 3 times. I found it and reported it to Adobe, and then it was used to win a hacking competition called Pwn to Own, and then it turned up in the Hacking Team dump. And in case people don't recall, Hacking Team was an organization that sold Flash vulnerabilities to a variety of customers, and they themselves got hacked, and then all their emails and exploits and source code got dumped on the internet. And in that dump, we found evidence that they'd had access to this bug and had used it to compromise people before it closed up due to being reported. So this is an example where finding and fixing a bug actually stopped attackers from using it. And the core issue here is that Actionscript II allows any method to be defined as any method. So if you say function1 equals function2, and then you call function1, function2 will get called. And this is what some people call monkey patching. And what makes the situation even worse is that when you call a function in ActionScript, it converts the parameter. You can pass in any parameter, and then it converts it. So let's say you need a string, and you pass in an object. It will call toString on that object. And that can cause a number of problems. So for this bug, what happens here is you create this class called a Convolution Filter. There it is. And then you create this other object. It's an object, and it has a function called valueOfDefined, and then you put it in an array. And then you call this vulnerable function. And what this vulnerable function does is it allocates memory and then tries to copy this array into the memory. And it has to be an array of floats because that's what image filters use. So it starts off, it allocates this float array, and then it tries to convert the array to floats. And it does this, but since this is actually an object with valueOfDefined, it calls valueOf, and then it calls the matrix setter again. And that's the behavior that the VM doesn't expect. So this starts the whole process over. It deletes this memory, and then it reallocates it and sets the pointer to it. And then this is a proper matrix with an integer in it, so it just sets that matrix. And then this function is done, but the previous call to the function still needs to complete. So that then writes to this freed memory, and this is a use after free. So another example of this type of problem is this bug, and this is an overflow caused by the same situation. So to start off, you create an array and you put stuff in the array, and this isn't especially exciting, but the interesting part is you set the length of the array to this object with, once again, valueOfDefined. And then you call this vulnerable function sortOn. And then what this function does is it starts off by checking if the array length is equal to 0. So it calls this function, and then this function returns 100,000, and that's not 0, so it continues. And then it fetches the length again, and it calls this function again, and then it returns 100,000, and then it stores it. Then it tries to allocate memory, and it fetches the length again, but this time you return 2, and it only allocates 2 bytes of memory. And I bet you can guess what's going to happen next here. It copies it into this new memory with the old length, and then that's an overflow. So another interesting bug that I found through code review is this bug in serialization. And there's a few interesting things about it. One is that this is another time where the bug was used maliciously in the wild. I reported this bug, and then 2 weeks later, it was found being used in the wild. And it's a type confusion in Actionscript III serialization, and I reported a few variants of it that all got fixed in this emergency patch. And also, I want to mention that this specific example does not compile. The code I'll show you is conceptual, but if you try this in your compiler, it won't work. So I had to create the SWIF with the correct bytecode by hand. So this is from the open source Actionscript VM. This is actually the real code. And you'll notice there's a check here. And what this check does is it checks if the binding equals binding none, and then throws an illegal override error. And what this is actually trying to do is make sure that you're not trying to override a function with something that's not a function. Like, you can't override an integer with a function. But you'll notice that this check has a very serious problem. It is commented out. So, just to be clear what can happen that should violate your sense of all things object-oriented programming, you have a superclass here, and you have write external defined. And then you have a subclass, and write external is an integer field. It's not a function. And so now let's go to the AVM some more. And this write external function, it does something very special in Flash. If you don't like what Flash serialization does, you can define this function, and then you'll override serialization. So if I define this function and Flash tries to serialize, it'll call write external and give me an object. Then I have to return the byte array, and then you also define read external where you get the byte array and give the object back. It's a serialization override. And then this part of the AVM is trying to do serialization using this override. So you can see, oh, it gets the function binding, but wait a sec, it's not a function, so that's not correct. And then it tries to convert it binding to method ID, which is just arithmetic, but that's not correct either because it's not a function. And then it goes out of bounds of this table, and then it calls a virtual method on it. So this is a type confusion vulnerability, and it's fairly exploitable because you're just calling the virtual method on unallocated parts of the heap that you can control. Another interesting type of bug I saw was exception bugs. And exceptions are actually very difficult to implement in virtual machines. I have my grumpy cat there because there's two ways to design it, and both designs are bad. Your one option is that, let's say you're in a native call, and you call into script, and the script throws an exception. You just keep going. And this is what Actionscript II does. And it has some advantages. The main advantage is that you'll never end up in a bad state, because since the code keeps going, everything you think will happen will happen. The downside is that developers don't think this is going to happen. It's kind of a counterintuitive behavior that you throw an exception and nothing happens. And while I've never seen a bug in Flash due to this, I have seen bugs in other VMs, so it can be problematic. Actionscript III uses the more intuitive behavior. If you throw an exception in Actionscript III, the stack actually unwinds and you exit from the native function. And this is more expected behavior, but then you have this problem of, did the developer think about every single time they called into script? Did they think what happens if the stack unwinds? And if they don't think about this every single time, then this can lead to bugs. So I've got two examples here. One is this bug, and it involves both script and the asset table in the Swift. So the Swift has this asset table that includes all the stuff like the font, videos, that sort of thing with inline types. And something interesting about this table is that it also has some reserved values. For example, FFF7 is an empty text field. And what's even more problematic is that you can override these. So if you declare your own FFF7, that takes precedence, and that will override the empty text field. So then what happens if you want to create a text field? Well, you create it, and then you create the object, and then it makes a pointer to this table. And at this point, this is actually OK, because you have the inline type. So it will detect this, and then it will throw the error, and then something weird it does is it will change the type to be of type text, and that's to prevent the error from spawning again and again as you shut down the player. But the thing is, I think they really wanted to throw a fatal error here because they didn't consider what happens if you can catch it. So you catch it, and then you create a new text field, and this time it creates the pointer to this font again, but now the type's been changed. So that's type confusion again. You're casting a text field to a font. Another interesting exception bug is this guy, and this is a use after free. You create this sound class, and then you create a byte array with 1,000 bytes, and then you call this vulnerable function. And what it does is it will try and copy this byte array into memory it allocates. So you can see that there. And this is actually a correct call. This one works properly. And then you create another byte array and you call it again. And this one doesn't work correctly. It deletes the buffer, but then it tries to load the stuff from the byte array before it creates the new buffer. Except this byte array is tiny. It doesn't even have enough bytes for one float, so it throws an exception. And now you have this dangling pointer. You can catch the exception, and then when you call the extract function, which extracts the sound data, you can just read memory off the heap. So another way you can find bugs is using reverse engineering, especially IDA, and complete citation needed, but I think this is how most Flash vulnerabilities are found. I've talked to other people who find Flash vulnerabilities and people that participate in contests, and almost all of the Flash vulnerabilities they've told me about, they say they found by reverse engineering Flash with IDA. The benefit of it is it finds deep and unusual bugs, the sort of thing you would never find through fuzzing, but it has an extremely long ramp up. People I've talked to have said, oh, they spent months looking at IDA before they had a usable image to start finding Flash vulns, and it is very slow. but it seems to be the way that most attackers find their bugs. So one sort of bug that was found through IDA is something I call MC use after freeze. And this was actually originally reported to the Chrome Vulnerability Rewards program, and the guy who found it confirmed that he definitely reversed engineered to find the bug. And it's the most common bug in Flash by far. Over 100 instances have been reported this year, and by this year I mean 2015, but it's a super common bug. It's really only one type of object that gets freed, but there's very, very many paths to this use after free. And the root cause of this issue has to do with how Flash display fields work. The problem with Flash display fields is if you delete one, you really, really delete it, even though it's a garbage collected object that has references to it, which is not how garbage collection is supposed to work. It's supposed to be if you still have a reference, you don't delete it, but this is a special case. And the reason they did this has to do with lag. Let's say you want to make a text field scroll across a screen. One way you might do this is create a text field, delete it, then create it a little bit over, then delete it, then create it a little bit over. And that'll look like a smooth scrolling text field. But let's say this is garbage collected. Then you create, delete, lag, create. So it doesn't make it as smooth. So to prevent this problem, they immediately delete the text field, but problems ensue. And more specifically, this problem happens when function parameters are converted after local variables are initialized, but before they are used. What does this actually mean? It means that you can usually avoid this problem by converting parameters at the beginning of a function. And actually, if you look at how browsers do this, the majority of browsers have a coding guideline that makes you convert parameters at the beginning of the function for this exact reason. And of course, it's sometimes hard to tell exactly what order a code does stuff, but this prevents the majority of problems if you always do early conversion. So to give an example of this bug, you create a movie clip, which is one of the vulnerable objects, and then you create a parameter which has toString defined, and then you call the vulnerable function, which is called swap depths. So you call into this function, and the first thing the function does is it initializes pointers to these two objects. And then it tries to convert the parameter, which is, of course, the wrong order. And it calls this toString function, and then this calls remove movie clip, which deletes the movie clip. And then the function will continue with dangling pointers to the heap. And this is the most frequent bug in Flash. Another way that I found bugs is with fuzzing, and I do this with my colleague Mateus. And we've done a few surfaces. We try and do the three main ones, which is Actionscript II, Actionscript III, and the Anticorpus. And we've only ever done mutation fuzzing. So basically, we scan the web for every Swift file ever that has existed, and then mutate them, change bits and bytes, and feed them through the Flash player, and then see when it crashes. Some people do generation fuzzing. I've never personally tried this, but especially with the movie clip use after freeze, once people discovered they were that common a bug, some people said they have written fuzzers that just generate code that's likely to cause that problem and have had success with it. With mutation fuzzing, it's very dependent on templates. So it's past the point where you can just take a Swift and fuzz it and find bugs. You need to find a lot of Swifts to find one bug. And we actually use code coverage measurements so that we focus on templates that have different code coverage than other templates to reduce the efficiency of fuzzing. What's challenging about fuzzing is it does find lower quality bugs. When you're looking at code review, when you see a bug, you can tell right away, is it a good bug, is it a bad bug? With fuzzing, especially in Flash, you just get so many null pointers and not especially good bugs. And this can be useful if you're planning on fixing every bug. But if you're just looking for the exploitable bugs, then it can take a lot of time. And one more thing I want to mention about fuzzing Flash is that the heap matters a lot. When we started off fuzzing, we weren't finding any use after free bugs, and we were kind of wondering why. And then eventually we realized that it was probably because the thing that was supposed to be in memory was still in memory, and it wasn't getting reallocated. So we changed it so that the heap had AC on it every time it was freed, and then that made a big difference, and we found tons of use after freeze. And if you don't want to recompile, another way you can do this is just create a frame in Flash that just churns and runs a lot of code and allocates a lot of memory. And that makes it a lot more likely that if you have a use after free, it will cause a crash. So here's an example of a bug we found through fuzzing. And that is the POC in its entirety, and I'm sure you can all tell exactly what's wrong there. what exactly is happening here is that when Flash calls a function, it allocates the args on the stack, and it uses alloca, and that has a minimum size of 8 bytes. So you have this allocated 8 bytes that has nothing in it, because there's no parameters to actually copy. And then you call this function convert to string on that, and that's uninitialized on the stack, so that means you're calling it on an unknown pointer. And the way this got found through fuzzing is that this function actually is supposed to have 1 parameter, but the fuzzing bit flipped that 1 to a 0, and then you had 0 parameters, and this caused the crash. So that's it for bugs. I'm going to talk a bit about how Flash exploits work now. And what were the problems when I started with Flash exploitation? Well, there are kind of 2 main ones. The first one is what I'd call generic exploit techniques. Up to about last August, almost every Flash exploit looked identical. And it got to the point where there were certain organizations who you could tell were using the same exploit code over and over and over with different bugs. You know, they almost never had to write a special exploit for a bug. There were techniques that were so well known and so reliable, they never had to write any new code. And that's not good, because you want attackers to have to take a lot of time to write their exploits, at least. And also, there were techniques that work with low-quality bugs. Usually, there's kind of a trade-off. Either you have a really high-quality vulnerability, and exploitation is maybe easy. Meanwhile, if you have a very low-quality vulnerability, you have to put in a lot more work to make stuff, make it exploitable. But there were techniques that even with not very good bugs, you could get really, really high reliability exploitation, and that was problematic. Yeah. And I also want to talk a bit about how Flash exploitation works. If you look at almost every Flash exploit in the wild, actually I would probably say every Flash exploit in the wild, the first state they want to obtain is read-write access to all of memory. And I think there's a few reasons they want to do that. To start with, it's a clearly exploitable state. If you always work towards that goal with a bug, you know, there is no doubt that you can exploit that bug if you can read and write to all of memory. Also, with regards to writing like a real exploit that's practical in the wild, there's a lot of benefit to that. You know, if you're just doing a POC, it's usually good enough just to show, oh, you can make a system call. But if you're going to like download malware or whatever else these bugs do, it really is useful to have read-write access to all of memory. So that is basically what every attacker tries to do with a bug. So the first way that attackers did this was using a class called the vector. And the vector class was extremely, extremely useful for exploitation. And this is because of a few things. It has this inline length parameter. So if you corrupt this length parameter and then access the vector, you can access all of memory. So that's kind of cool. But more importantly, it's variable type and variable length. So no matter what type of object you can overflow, you know, be it a big object or a small object, be it an integer or an object, you could make a vector fit in there, and then you could corrupt it. So this made this a very reliable type of exploit because, you know, no matter what your bug was, you could find something that would fit into the slot that got corrupted and then corrupt this length. To give an example of how this worked with use after free, it's kind of the same deal. You have this dangling pointer, and because this object is so versatile, you can almost always find one that fits into the area that was used after freed, and then you can just write to this length, and then that allows you to access anywhere in the vector, read or write out of bounds. And that helps a lot with exploitation. So the first mitigation that went into Flash, and this was last August, was the vector mitigation. And this did 2 things. It added checksums to vectors. So now if you corrupt the length of the vector like you do here, the next time you try to access it, it will check a checksum, and if that checksum isn't correct, it will fail gracefully. So this causes a crash. Also, some vectors are put on their own heap page, and that means that it's less likely that you can find a bug where you can corrupt a vector in the first place. And this did 2 things. It started off by reducing the reusability of exploit code. Everyone who had been using the same exploit code for years now had to write some new code. Also, it generally increased the quality of bug needed for an exploit. There were some exploits in the wild where the bug was like super low quality. Something like you could change 1 bit of some specific object that was used after freed, but because you could shuffle it so that that length was at the beginning of that bit set, you could get the full read-write access to memory. And this means that, you know, it's usually harder to exploit a bug like that. At the very least, it's a lot more work. And some people say that you can substitute the byte array or the bitmap data for the vector object. And this is totally true, but it's not as good. What was good about the vector is it was variable size and variable type. Meanwhile, byte array and bitmap data are static size, static type. So you need a better bug. You either need a bug that happens to be that size and type, or one that's variable size or variable type to make exploitation work. So after this mitigation went in a couple of months, there was a 0 day. And that was the one I showed you with the commented out check. And this one was still exploitable with the mitigation, and it was exploited using the byte array. Because the traits array that you were indexing outside of was variable size, it was possible to get it to be just the right size that you could allocate a byte array in there. So they used this to get read-write access to the entire memory space. So at this point, the second mitigation set went in. And this had a few different things in it. The first one is what we call the ISO heap. And this splits the heap into 3 partitions: a pointer partition, a non-pointer or data partition, and a dangerous partition. The dangerous partition is for objects that have a history of being used in exploits, for example, contiguous data types. And this helps prevent exploitation, mostly just because it causes a bit more heap entropy, but also because most exploits on some level involve confusing data for pointers or confusing pointers for data. And if those are on separate heaps, then that gets a lot harder to do. And of course, this isn't really perfect. Most objects have a combination of data and pointers, and you have to decide where to put them. But this is a good first step, and it does make certain types of exploitation a lot more difficult. And the other thing the ISO heap included was also increased segmentation by size. So depending on the size of a block, they're all on different heaps as well. They also put checksums on the byte array object that got used in the previous exploit because they knew attackers were using it. And they also implemented something called JIT spray mitigations, which basically makes it a lot more difficult to use the JIT to generate a ton of code that you can just stick the instruction pointer into. And it's actually been several years since there was an exploit like that in the wild, but they decided to put in the mitigation anyhow, just in case that turned up. So after this, the first exploitation we saw was a OneDay. And a OneDay is typically used by certain financially motivated attackers. They don't have 0 days, but as soon as Flash issues an update, they will create an exploit for it and then put that in the wild and then use it for stuff like ransomware. And usually these aren't especially interesting, but in this case, it was because it was the first time we saw someone exploit these mitigations. And the way they did this was they had this bug, which was a controllable size and also a controllable size of an overwrite. It was an overflow. So they were able to fit in the last remaining type that accessed contiguous data, which was the bitmap data type, and then they were able to overwrite the size and get read-write access to all of memory. And then there was a second 0 day that turned up in the wild. This was used for a very targeted attack, and it was a heap overflow vulnerability. And what was very interesting about this exploit is that it was a Swift that actually contained 2 exploits. One was the typical vector exploit that I described at the beginning, and the second was one that worked after the isolated heap. And here is what this exploit involved. Long if statements nested almost 100 times, using both a media file and an image file to fill heap slots at different points in the exploit, triggering the bug almost 600 times, and then eventually they were able to correct the checksums of the byte array and get read-write access to all of memory space. So there's kind of 2 things you can learn from this. On one hand, the mitigations didn't really prevent exploitation, but on the other hand, they had to really, really want to do this. This was so much more difficult than the original exploit. So then we moved on to ISO Heap 2, and this was a few changes. There were some subtle changes in heap partitioning, moving even more objects to the dangerous partition so that it was less likely they could be used in exploits. And also, the bitmap data object, which we believe is the last contiguous object, was checksummed. And then also extendable checksumming was implemented. So now if another type of object shows up in a 0 day, Adobe can very easily add checksumming right away. And then a final, I don't know if this is actually a mitigation, a final feature was zero freeing. And this came out of the fact that there were a few use after frees where you would just look at them and be like, how did this possibly not happen in normal use? And the truth was they were happening in normal use, just the right thing was always on the heap, so no one noticed. So the point of zero freeing is just a detectability mechanism. If there is a use after free that's happening in normal use, you're now going to notice because you'll get a null pointer exception because everything was zeroed out. So at this point, this set of mitigations went in, and we didn't see a 0 day for a while. So I started writing an exploit for it just to get an idea of what the next set of exploitation might look like. And I used 2 bugs for this. The first one was this Unwatched bug. This was the one we found through fuzzing, and it's very unintuitive, and it's because you're missing the parameter of the unwatch. And just to review, you get the alloca, which is an uninitialized variable on the stack, and then you call convert to string on this variable. So you can basically control where this converts to string thing gets, what it gets called on. And to go into more detail, what does the string conversion function actually do? Well, the first thing it does is it checks to see if the pointer ends in 6 and then returns if it doesn't. And this is kind of a weird thing to do. The reason it happens is that in Flash, and actually I would say in almost all ECMAScript implementations, the unaligned bits of the pointer are used as a type check. So 6 means it's an object, and then there's different values for, say, an integer or a string. So it does this type check. And then if the type check passes, then it casts this to a pointer and then calls the virtual call on the pointer. So if you think about it, there's a few different ways you could try to exploit this. And one thing, if you look at this bug, it's almost certainly exploitable if ASLR is bypassed. ASLR is a mitigation in most executables where things like libraries and the heap and the stack get loaded at different locations. And if you imagine a situation where that didn't exist and you knew where everything was loaded, then it's fairly easy to put a pointer on the stack, like an absolute pointer, and then make a virtual call into something you know stuff about. But in this case, since I don't know, that's going to be a bit of a challenge. So there were kind of 3 options I thought of here. The first one was, let's say I initialize the stack as an absolute pointer. Well, that one, you definitely need to bypass the ASLR separately. There's no hope there. The second one was, what if I initialize a valid pointer on the stack of the wrong type? I kind of thought there were 2 ways I could do this. The real challenge here is that this needs to be a pointer that ends in 6. And when are you ever putting a pointer that ends in 6 on the stack? There's 2 different situations I thought could happen in Flash. One was maybe with a string buffer. If you're iterating through the string buffer, maybe you get this unaligned pointer on the stack, and then you can set the contents of the string, and maybe that's okay. But I didn't think this would actually work, because the problem is that for 8-bit pointers, they have a lot of zeros in them. Meanwhile, in Flash, most strings are UTF-16, which means they terminate if you have 2 zeros in them. So I didn't think I'd be able to get very many pointers in that string, so I don't think this will work. The other option was to do the same thing with a bitmap. What if you're calculating the pixels? But the problem with bitmaps in Flash is that they do a lot of color correction. So your image is kind of always churning with being averaged and that sort of thing. So that seemed unideal for pointers as well. So I didn't think that this would work, or at least there were very limited options that might not end up turning out. So the other option is that maybe you could initialize the stack with a stale pointer. Maybe you could put an object on the stack and then wait for the object to be freed and then allocate it as something else and then do this call. And I thought that could work, but the ISO heap actually really prevented that. Because there's now the type splitting and the size splitting, there are actually only 2 objects in all of Flash that would fit into the same heap slot as an object that ends in 6 that gets freed. So when I tried both of those, they were both very boring objects that I couldn't do a lot with. So this was prevented with the ISO heap. So at this point, I accepted that I'm going to need to use another bug here. There's no way you can use this bug on your own for exploitation, or at least I couldn't think of one. But if you bypassed ASLR, you could use the first option, which is absolute pointer. So I added in this other bug, and this is the one that has to do with exception handling. Just as a quick reminder, you create a sound object that has the buffer, and then you call the function that throws an exception and it frees the buffer, and then you can just read data off the heap. So this is a nice info leak that I thought you could use to bypass ASLR. But of course, once again, the ISO heap gets annoying here. There was not a lot of stuff that you could read off the heap that had pointers in it, because the sound waves are data. And after a lot of effort, I eventually figured out there was one thing I could access on the data heap, and that was when Flash calculates JIT, it sometimes allocates stuff on the data heap, except these JIT objects are virtual, so they have a vtable. So I managed to make a sound thing that was just the right size, that one of these JIT calculations would end up where the unallocated memory was, and then you could read the vtable. And that was nice. Once I was able to read a vtable, then I could bypass ASLR and figure out where everything was. So that was good. But the next thing I really needed was a contiguous buffer. Because a good way to exploit this bug with the absolute pointer is that you create something that looks like a fake C++ object, and then you have a fake vtable there, and then you create a fake vtable that then points into different memory that you can ROP. But this was hard to do on the ISO heap because all the contiguous data types are on the dangerous partition, and the info leak I had was in the data partition. So I needed to find a way I could find a buffer and know the location of the buffer on the data partition of the heap. I ended up looking through all the Flash functions and using a combination of two functions. So to start off, there's this function called determine preferred locales. And what this does, as a part of the processing it does, and these are just temporary structures, is it creates an array of character pointers, and then it makes each of these character pointers point to a string. And what's kind of interesting, what makes this a really useful function, is that you can change both the size of the character array, like the number of strings you have, and the length of each string. So I was able to make it so that this character array fit into the same slot that was freed by that sound bug. So that was good. Then I was able to read out the location of this pointer. So I would read this pointer, and then at that point it doesn't really matter if this is freed, because you know the location of the string. So then this function exits, and also the string gets freed. But that doesn't matter. You still know the location of that string in memory. So then I called this other function palettemap. And what this does is it creates a palette, so basically a color array in memory that you can use to define different colors in Flash. And this is nice because this array is an integer array, so you can control every value in it. It's a contiguous array. And I called this in such a way that it was guaranteed to take the same slot as this string that had been freed. So now you know where the pointer is because you were able to read the pointer, and you know where the string is. So this is how you can get an array you can control with a pointer to it. And so I had this, and I'll explain what this stuff means in a sec. For this exploit, it was really useful if I could get two buffers, but once I had this technique, it was easy enough to just create a second buffer using exactly the same technique. So you have a buffer with a pointer to another buffer. So this is good. I have my structure for the exploit set up. The next thing I needed to do is trigger the bug. And, once I got to this point, I realized it would have been better to think about how I was going to get an absolute value on the stack before I did all that. But I was now at this point and had to figure out how to get an absolute value on the stack. And eventually I figured out that one way to really do this with a lot of the stack was that if there is a small string in a SWIF and it gets converted to UTF-16, this is actually done on the stack. So I made a SWIF that does this. And the unfortunate thing is that this doesn't work with dynamic strings. So if you say like var a equals string, this won't end up on the stack. But if your string is actually in the SWIF, this will end up in the stack. So what I ended up doing was making a Python application that would generate a SWIF. So I started off with the SWIF that generated that structure, and then this would make a call with the pointer location of the structure into this other Python script that would generate a new SWIF that when you called that would put the right things on the stack, and then it would trigger the bug. And then just to run through how this works now that everything is set up. So you trigger the bug, and it checks whether the pointer ends in 6, but you set the pointer, so it does. And then it does this call on it. And you start off with this first red array from the palettemap. And this is a virtual call, so it looks for the v table and then goes into the second array. And for this specific call, it starts off in the middle. And this will put the beginning of the array into the this pointer and then call later in the array, which is 28, which is system. So this leads to a system call with a pointer to the beginning of this array. So that will allow you to call one system command and at least prove this exploit works. So this is what I came up with to bypass this mitigation. And of course, as soon as I did this, but before I released it, someone else, or a 0-day turned up in the wild. And what was interesting about this one is that it didn't actually work. So it was reported by Trend Micro, and it was in the Magnitude exploit kit, which is another financial exploit kit that is used for things like ransomware. And the bug in there was not fixed. But it only worked on old versions of Flash, and that was because the people who had written this exploit weren't able to make it work with the new mitigation set. So that was kind of cool. The 0-day was reported, but even though they had an unknown bug, they couldn't make it work. The mitigations had stopped them. So that was interesting. But then there was another 0-day, which did work. And this was a targeted attack reported by Kaspersky, and it used out-of-bound array access. It was an out-of-bounds array access, and it used the similar vtable attack to what I did. So, we're still at the point where the mitigations are working a bit, but we're 1 for 2. One set of attackers was stopped, but the other one wasn't. So, what do I think this all means? Overall, I think reducing bugs and mitigating exploits has made it more difficult to attack Flash. We've seen some evidence of this. One thing we're seeing is more complex exploits. It used to be that every single exploit was a vector exploit, but that's not the case anymore. We've seen a lot of new techniques because attackers have been forced to move to new techniques as their old ones have dried up. We've also seen exploit kits using other bugs. And you don't always see this when you're just looking at the Flash 0 days, but what's interesting is what's not there. When we started off, for every single Flash update, there were these exploit kits that would find a bug and then update their exploit kit and exploit it. And now a lot fewer exploit kits are doing that. In fact, a lot of them are moving to other bugs, for example, Silverlight, other vulnerable software. And also a lot of them are not working. It was like basically quite a long time ago that they issued their last update and they haven't been able to get another working exploit. And that's fairly good. So it seems that at least a lot of these financially motivated exploit kit authors are having a lot of trouble now, and this is actually preventing them from mounting their attacks. And fundamentally, mitigations are a cat and mouse game. You can't expect that you'll put in a mitigation and you'll never get an exploit again. The real goal is to slow down attackers, make it so that there's fewer 0 days and they have to spend a lot more effort, and that seems to be what's happening here. I would say finding bugs has become a lot more difficult. As I said, I'm down to 1 bug per week versus 1 bug per day. And what's more interesting is that whole classes of bugs are starting to disappear. There were kind of 2 classes of bugs that I showed. There was the ones using the value of, and then there was the movie clip use after freeze. And those are both types that there were tons and tons of reports of, and now they're basically down to 0. It seems that once a certain bug class becomes popular, they start to all get found and get fixed. And Adobe has also done a few wide-scale changes to make them more difficult to find and less likely to happen. And it means that these bug classes are basically going away. Another thing I've been seeing is more bug finders. There's a lot fewer people now who are finding 10 bugs every update or huge batches of bugs. Now a lot more people have become more interested in the area, but it's usually each person is only reporting 1 or 2 bugs. So I think this is another sign that they're becoming more difficult to find. And a final thing is that we've also started seeing lower quality bugs and exploits, things that maybe even a year ago is not the bug that the attacker would choose, but now as they're getting more picked over, they're starting to be used. So I think there's some progress here, though I think what we're all really hoping for is Flash deprecation. And I think it's going to be a few years now, but that's probably the future. And I think what this will mean is that attackers will move somewhere else. Personally, I'm moving to browsers because that's what I think the next area of attack will be. So that's it. I want to end off by thanking Adobe. They have been super helpful with this research. They, of course, implemented all the mitigations and have also fixed all the bugs. And they have a very difficult task, and I think they've done well with it. And that's it. I'd now like to open the floor for questions.
I'm Rick Farrow. So this reminds me of showing up for USENIX security 3 years ago in Washington, D.C., riding the subway, and there's a big poster in there, and it says, Adobe owns Washington. And, of course, to my mind, it means, yes, Flash owns Washington. What do you think of you describe the language? I'm just appalled. What do you think the people who design Actionscript in the first place, they don't seem like they're language designers. You know, they're certainly not people designing Go. They're designing something very strange. I mean, like the ability to redefine a method, a lot of very strange things. Could you comment on that? And also, how many lines of code is Flash currently?
I'll start with your second question.
Yes,
I don't really know, but I think it's about more than a gig of code. So I've never actually counted, but it's very, very large.
Yeah, okay. It's hundreds of thousands of lines of code, let's say.
Yeah, and with regards to Flash, I think it's actually blame ECMA. There's nothing they've really done that is not in the ECMAScript standard. The things like, you can redefine stuff, you can convert stuff. None of this was their idea. It was all the ECMAScript standards idea. And I think part of what happened here is, what AS2 I think was ECMA 3, and then they defined ECMA 4 as AS3, and then ECMA 4 never got adopted. So AS3 actually doesn't have these problems because they realized they were having them, but AS2 is now implementing this really difficult standard that isn't being kept up to date because it's not an active, it's not a language that people are actively writing code in. So I think, browsers do theoretically have the same problem. Everything you can do in Actionscript, you can do in JavaScript. It's just because, I guess, that code is still alive and people are still writing scripts for it. It's, better maintained, and, some things have been redesigned. And I mentioned coding styles that force you to move conversion to the top. Those are all the things you can do to prevent it. And I think Actionscript 2 is just in this space that it's almost abandoned, but not quite, that all that good stuff didn't happen, and then you ended up with all these problems.
Okay, thanks.
Hi, Jeremy Epstein, DARPA. Really interesting talk. I wanted to actually go back to something you talked about almost at the very beginning, where you said that the good news is when problems get fixed, they stay fixed. And when I heard you say that, I was reminded of something from the Mythical Man Month. I don't know if you've ever read that book. It's one of the great books of software engineering, about 40 years old. And they did studies and concluded that fixing bugs beyond a certain point, every time you fix something, you break something else. And so I was kind of surprised when you said that when bugs get fixed, they stay fixed. I was wondering, have you seen any evidence either that new bugs do get introduced as they fix things, or conversely that they've broken the cycle that was noted 40 years ago?
Yeah, I think that was a bit of an exaggeration. I would say that 98% of bugs, when they get fixed, stay fixed. We have seen twice where adding in a fix out of 100 bugs did cause another vulnerability. And I think, maybe that rule doesn't necessarily apply to security bugs. What I care about is that the vulnerability goes away. I don't care if anything works. That's probably bad, but that's kind of my thought process here. And I think maybe the likelihood that fixing a vulnerability will add another vulnerability is less than fixing a vulnerability will add another bug. Because there also have been some vulnerabilities where we just had to accept that it would break a small number of Swifts. As an acceptable cost, there was no way to fix it without breaking Swifts. And that has happened in a small portion of bugs too. But at some point, you can't leave vulnerabilities in because they'll break
I'm
stuff.
certainly not arguing for leaving vulnerabilities in. It's just like Windows, I don't know, XP or some of the earlier versions. After a while, it seems like Microsoft sort of threw up their hands and said, "There's nothing we can ever do that's going to redeem this pile of crap. We need to start over." And I wonder whether that thought has occurred in Adobe, that this is beyond hope. We need to start over both with a redesign of the language and a redesign of the implementation. Right, of course,
Yeah.
but
I'm serious.
Yeah, no, I think he's actually. Yeah, I think deprecation complicates this for sure. If they were thinking of 20 more years of Flash, my guess is that a rewrite would be in the cards. But right now, because they know there's no active development, it's just a matter of, what can you do? And I think without the option of redevelopment, fixing bugs is better than not fixing bugs.
thank you.
Adrian Felt, Google. So you found an enormous number of bugs, primarily through code review. Why didn't Adobe find them before shipping the code? That seems like that would have been the ideal time. Is it because they weren't reviewing the code at the time and looking for these types of bugs, or is it because they lacked the kind of security researchers who could find these bugs?
That's a good question. I think there's a few aspects. One I think is kind of a staffing concern. Not everyone can find these types of bugs, and it's hard to find people who can. I think also early on there was some disagreement about the importance of these types of bugs too. Some people ask the question of, well, if we can never fix all of them, is it worth fixing any of them? Yeah, or maybe it's just better to wait for them to turn up in the wild. And I don't agree with either of those statements. But I suspect that some of what happened was a concern that, if we can't fix the whole problem, maybe we shouldn't try fixing the problem at all. And I don't think that's the right thought process, but I suspect that might be what's behind some of it.
Are there any additional questions?
Can I ask one more?
Sure.
So, when you find these bugs, are they more for one platform than another? I guess that's sort of a naive question, but what comes to mind is that when I started looking at NT security in '98, I noticed they had a system call that said, download this file, and once you downloaded the file, the next system call would be execute this file. And so, to my mind, this made exploitation of Windows systems really easy. Mm-hmm. So is there any kind of relationship between Flash and the platform that's easiest to exploit?
Yes, there is. There's kind of two subsets of this. One is there are actually platform-specific bugs in Flash, and it's actually fairly rare to see them used in the wild, but we have recently just because I think the bugs are getting picked over. So that does occasionally happen, though I think that isn't any likely to happen to one platform over the other. It's just kind of random chance which ones ended up with the bugs in them. But with regards to exploitation, we do see OS differences and browser differences. With regards to OS, it is usually targeting Windows just because that's where the popular targets are, especially with things like ransomware, malware. I think because so many people use Windows, that's what they pick. Also, we find a browser differential. I'd say Chrome and to some level IE are the least likely to get exploited just because of sandboxing, and now IE also has some mitigations related to freeze that make it harder.
Well, thank you. Appreciate it. It's an interesting look into something I've always wondered about. Thanks.
Let's thank the speaker.